Danucci, and I've been a safety engineer and consultant for over 20 years now. So when I decided to start my own business, I was wondering what I was going to call it. And I looked around at various names, some of which were already taken. And I came up with the name, The Safety Artisan, for the business and the website, safetyartisan.com, if you want to take a look. And I came up with that name because I liked the word artisan and what it meant and the connotations. So first of all, I mean, artisan means a skilled person who does something by hand. And it can also refer to a thing that is, specially handmade, usually with high quality materials. So I like the sound of that. And I think it's appropriate, even in this modern age where I've worked on, huge projects, multi-billion-dollar projects that lasted for years and involved thousands of people. Because even on a big project, we're still relying on individuals being competent to do a job and to know how to do it, and to have that skill and that awareness and that understanding. So that artisanship, that appealed to me. I thought that's good. And another thing was that there's this connotation of somebody working alone at home, maybe a sort of a cottage industry type setup that used to exist before the Industrial Revolution. Or I should say, before the first Industrial Revolution. Now, whichever Industrial Revolution we're currently in at the moment, I don't know. But we've gone back to a world where, thanks to the internet, you can sit at home and do work. And in fact, thanks to, the recent global pandemic, more and more of us have been sat at home doing work, working remotely over the internet. And I, as an individual, can reach hundreds, thousands, or even millions of people over the internet with my teaching and with my knowledge and experience. So, the internet has really enabled a return to those kind of cottage industry ideals where individual people can do something of high quality and find a market for what they're doing, regardless of, big brand, big business, etc., etc. So we can, you and I can communicate one-to-one or one-to-many, and you can communicate with me, and we can learn together and share together what we want to do. Now, if that sounds good to you, if that sounds something that you're interested in, then please check out the videos and other learning products at safetyartisan.com. And you'll also find me, Simon Danucci, on udemy.com. So if you want to see what I do on a third-party platform, and then that's there too. Okay, well, thanks very much. And I look forward to seeing you again soon. Cheers. Okay, well, that's enough of that. Welcome, everyone. It's good to see a few people have dialed in already, dialed in early. That's great. Good to see you. And no doubt we've got some more on YouTube live, on Facebook, on LinkedIn, and on X, the social media channel that was formerly Twitter. Oh, somebody else has arrived. Yeah, that's terrific. So first of all, can you all hear me okay? Can somebody give me, send me some text just to make sure that you can hear me?
because it's very embarrassing if I talk for an hour and the microphone isn't working. Oh, that's great. Thank you very much, Cheryl. Thank you. Terrific. Okay, so today we're going to be talking about, oh, thank you too. We're going to be talking about cause analysis or causal analysis, and let's get straight into it. So I'm just going to share my screen. Okay, so you should be seeing the first slide. So in cause analysis, in this webinar today, we're going to do three things. We've got some basics to talk about, the most popular causal analysis techniques as sort of voted for by the great international, global, World Wide Web public. We're going to have a Q&A session about that, and in fact we can talk about anything you want to. And then I've got a sort of a deeper dive into looking at data for causal analysis and the kind of things that we might do depending on what data we've got access to. Okay, but I'll repeat that in a moment. So that's what we're going to do. So first of all, just a little plug for myself. I say, oh, why should you listen to me? Well, I've been doing system safety engineering for a long time, about 25 years. I've done it in various different domains, in different countries, and I've worked on some huge programs and some very small ones, which has been great, actually. Oh, somebody else has just arrived. Thank you very much. So I've done a lot of different things, and I've done it. I've worked in the UK. I've worked in Australia now for more than 11 years. I've worked in Europe, continental Europe, and I've worked on a lot of American systems. Okay, and I've worked with international partners. Okay, so we've done things to international standards, to national law, all kinds of stuff. And hopefully that will give me a nice broad view of safety. And because I mean, sometimes you encounter a safety practitioner who's only ever done anything one way. They've only worked in one industry, and they can be a bit narrow. Okay. I acknowledge there's different ways of doing things. Nobody has got all the right answers. There are things in my career when I thought, well, we didn't do that very well. We could have learned something from these people over there. Anyway, that's me. So before we go any further, if you're new to hazard analysis, safety analysis, I just want to, with one picture, explain some basic terms. So the idea when we're doing safety analysis is we have hazards, and as the sort of bow tie diagram suggests, one hazard can have many causes and one hazard can have many consequences. So it can have a range of consequences. Now, some of those consequences will be harmless and some may result in harm to people. Okay, and that progression from causes to hazard to consequences is known as an accident sequence. Okay, so we're looking at the worst case scenario where somebody gets hurt. And it's not really important for today, but the test for a hazard is it's necessary for the accident. If there's no hazard, there's no accident, and it's enough. Once the hazard is present, nothing else weird or unusual needs to happen for the accident to occur. Okay, so the hazard is necessary and sufficient. And I've mentioned about consequences. There are different consequences, but today we're talking about causes. Okay, so we're going to talk about analyzing that left-hand side. That's my left-hand side of the bow tie. So let's move on. So as I said before, what we're going to cover, we're going to look at the 8 most popular causal analysis tools, techniques, methods, call them whatever you want. I don't really care, as chosen by what people look for on the internet or on Google specifically. So I'm going to present some information about that. I'm going to make some commentary about that. And I say sometimes cynical. I look at some of these techniques and I think, yeah, okay, there's not really much substance to this, but nevertheless, it's it's always worth looking at or incorporating into something else, let's say. And we're going to look at some resources that are out there. So then we're going to have a Q&A session. And while we're doing the Q&A session, I'm going to share some useful resources and links with you in the chat, okay, while you're thinking about your questions. And then in the third section, which I think is the most interesting, we're going to take a deeper dive into some data for causal analysis, just to illustrate some examples of what can be done, okay? And we're going to be looking at the European Maritime Safety Agency, or EMSA. We're going to be looking at one of their annual reports, okay, which is really very, very good, an exemplar of how a regulator, in my view, should report. Okay, so part one, let's look at some popular methods, which are, excuse me a sec. I'm sorry about that. So, which we get from the internet. So, I'm not sure whether these really all qualify as causal analysis methods, but this is what we get. Okay, so we've got Pareto charts. We've got FAMIA, failure mode and effect analysis. We've got 5 whys. We've got Ishikawa fishbone diagrams, fault tree analysis. We've got 8D report or 8D reporting. They've got the DMAIC template and scatter diagrams. Okay, and I'll mention this again, but I've already done a webinar on FAMIA, and you can see that on my Thinkific site. So all the webinars are recorded and go on the site. They're part of the Safety Engineering Academy. And I'm going to do one on fault tree analysis. I think it's in July. Is it scheduled for? So we're going to do one all about fault trees in July. Okay. So those are the 8 top tools, pot pickers, that we're going to look at. And okay, so let's start with a Pareto chart. Now, interestingly, I saw in a video the other day, Pareto didn't actually invent this. He discovered somebody else's, the original inventor, and championed it. And now we all think it was his, but it wasn't, apparently. Anyway, never mind. So I suspect most of us have seen this before. If we look at the causes of a certain outcome, and in this case, we've got an example of types of medication errors, what we often find is that a few causes are dominant. Okay, so in this case, dose missed, wrong time, wrong drug, really, and then overdose gets us, 70% of the causation. Okay, and everything else is only 30% in this example. Now here they've drawn a line at 80% of the cutoff, because sometimes Pareto is known as the 80-20 rule. Okay, and that's suggesting that maybe 80% of the outcome is caused by 20% of the inputs or causes. Okay, so most of the output variable is driven by only 20% of the input variables. Now, that's an approximation. It doesn't have to be 80-20. It might be 70-30 or 60-40. It doesn't really matter. The point is there are some dominant causes, okay? And of course, the obvious application for this is if we can identify the dominant causes, then clearly, if we work hard on just those 2, 3, 4, 5, whatever they are, then we can get a disproportionate reduction in risk by concentrating on those few things. Whereas we could spend an awful lot of effort at attacking all the other causes and make very little difference. So clearly, very simple technique, but just being led by the data, we can make life a lot simpler for ourselves. We can become far more effective at risk management. And clearly, obviously, not just safety risk. And of course, it's a very simple technique. We really don't need much to do there. So moving on, we can talk about FAMEA. I'm not going to say much about FAMEA because, as I said, I've done a whole webinar on FAMEA, which actually was my most popular webinar ever. It was completely sold out. So thank you for all those who dialed in. And it's a technique dating back a long way, back to the 1940s from the US military, where, as the name suggests, we look at failure modes, the different ways in which a design or something might fail. It might be a design, it might be a service, whatever it might be. Okay, and then having looked at those failure modes, we then analyze the possible effects. Okay. And as it says, there's a family of analyses out there. There's FAMEA, there's FAMICA, where we add the C stands for criticality, where we add more detail into the FAMEA. And there's also things like functional failure analysis, which is similar but simpler. Okay, you only need functions for that. You don't need a design or an implementation. And as you can say, you can get it at the Safety Engineering Academy. I'll put the link in the chat when we're having our Q&A session. So very powerful technique, very widely used. Lately, I've seen some people having a go at the technique and saying, "Oh, it's broken, it doesn't work." Well, my simple answer to that is twofold. So first of all, use the right technique for what you're trying to achieve. Okay, so understand what your objective is and then use the right technique. If FAMEA is the right technique or near enough, if it gets you 80% of the way there, that'll do. Choose that and then learn how to do it properly. Okay, so if you do the right thing and you do it right, you'll get good results. Okay, doesn't matter whether it was invented 80 years ago or 8 minutes ago. Okay, let's not get too much into fashion in safety. I've seen a little whinge here. I also work in software engineering, and software, sadly, is very driven by fashion. And I've seen so much wasted effort, people chasing after fads, trying to, make a difference when it doesn't really. Whereas maybe, if they'd done the old Pareto chart and gone, "Oh yeah, we're spending a load of effort fiddling with stuff down at technique errors. We're wasting our time. That's only accounting for a tiny percentage." So let's look at facts and statistics and reality, not fashion. Right, sorry, end of whinge. Okay, next one is 5 whys. Now, this is one of these things that I think, in a way, is a bit something of nothing. Okay, which is probably going to upset some people, but I don't really care. And yeah, okay, you just keep asking why. I've got this result. Why did that happen? Okay, it happened because of this. Well, why did this happen? Well, it happened because of that. Why did that happen? So all you're doing is you're unpacking that accident sequence, that causal chain of events. Yeah, that's all you're doing. You're just unpacking that. You're asking one very localized question. I've got this result in isolation. Why did that happen? Oh, it was triggered by this, which was triggered by that. So there's a bit there's not much to it really, but it's a good technique because actually what we need to do when we're doing more sophisticated techniques, I can't even say the word, when we're doing cleverer stuff, we need to use this approach because with a lot of analyses, fault tree analysis, event tree, whatever it might be, what we need to do is focus very tightly on a result, and then we just need to take one step back or forwards only and say what caused that or what could that lead to. Okay, because a very, very common mistake, and I've seen it again only this week, is people try and leap to a solution rather than taking one step at a time. Okay, and that's how you make mistakes, and that's how you confuse yourself. So in a way, this is really good practice. Learn to take baby steps when you're doing the analysis. Why, why didn't a light bulb come on? Well, either the light bulb was broken or because no electricity, there was no voltage at the light bulb. Okay. Why was there no voltage? Well, either because the wiring had broken or because there was no supply from the switch, and so on. Instead of trying to leap to, oh, the electricity has failed, okay, in which case we miss a load of stuff. Let's do that. Okay, so more people arriving. Welcome, welcome, welcome. So that's 5 whys. Useful mini technique, I would say. Okay, Ishikawa diagrams. So an Ishikawa diagram, or a fishbone diagram, as it's often called for obvious reasons, is a causal diagram. And it's often used, we might use it in accident investigation. I remember being taught how to do this, and we use the example of the Piper Alpha oil rig disaster, which was grim, but there was a lot of causal analysis to go into. And whether we've got some groupings here, as you can see: equipment, process, people, materials, environment, management. Whether we use those groupings or not, or we just go with the data that we discover, it doesn't really matter. But we can use it to investigate accidents. We can use it to say, okay, I've identified potential outcome or problem that we don't want. What could contribute or cause that? Okay, how could we move backwards and look at what might cause that? And of course, the great thing about this is that it's prompting us not just to look at technical problems, just equipment, that's just one of the 6 groupings here, but it's actually asking us to look at the bigger picture, the sort of the socio-technical environment. Okay, so for complex systems, this is great because it prompts us to think about all the different things that might contribute. And as you can see from the diagram, we've got primary causes directly joining the main fishbone going into the spine of the analysis, but we can also have secondary causes that cause the primary or contribute to the primary. Okay, or indeed, in theory, I suppose we could have tertiary as well. But to be honest, you would need a tool to do that, I suspect. Otherwise, you get a bit confused. But this is great for brainstorming. You put it up on a whiteboard and then think about it a bit as a group. Is a great way of getting a group to focus on something. And then you might record all of this more formally in a tool or in a document, whatever it might be. So really powerful technique for complex systems. We could probably do a whole webinar on this, actually. So fault tree analysis, and as I say, we'll have a webinar devoted to FTA in July. So basically, for those who are not familiar with fault trees, we at the top, we have a top event, and that top event might be a hazard, or it might be a particular failure mode, whatever it might be. and then we look at what might cause, what might contribute to that top event. Okay, so in this particular example, we've got, I think it's a ship is leaning over, what do we call it? Is inclined, whatever we're calling it. And it says, okay, there are three things that could cause this. We've got a failure of a pontoon, whether it be left or right, port or starboard, or we've got water has been incorrectly, shifted from one pontoon to another. So clearly in this, we've got a platform sat on two pontoons that can take on water. And then we've got some more ore gates. So the green OR 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 gate, they're called gates. And we've got an AND gate down below. So for the AND gate, for the crossover valves, that problem, then both the left hand and the right hand events have to happen in order for that gate to work, to fire. Okay, whereas for the OR gate, only one of them needs to. Okay, and as it says, this is the same logic as a reliability block diagram, but the other way. In an RBD, we're looking at the top event is success, whereas in this one, the top event is failure or non-availability. Okay, we might be doing a reliability or a analysis saying, okay, what could cause this lack of availability of the system? It might not be a failure, it might be something broader than that. So there's your basic technique, very, very popular technique. And there's lots of tools out there, several domains, particularly aviation. The regulators will specify that you have to do fault trees for equipment with numbers. So they've got to be quantitative fault trees. And to do that, you've got to have a tool basically to do the maths for you and to keep track of if you've got a large number of events and gates, then you really need a tool to support you in doing that. Okay, and there are plenty of purpose-built commercial tools out there of very good quality. Okay, so another popular technique, great for complex systems, and we can look at the effects of multiple failures. You can also get a lot out of it just from a qualitative approach. Okay, so for example, on this one, we can see we've got three OR gates. So basically, if the let's get there we go. So if this event happens, then that will percolate all the way up to the top. So as soon as this happens, that's going to be the result straight away. There are no barriers, there's no protection with these OR gates. Okay, so as soon as this happens, that failure will propagate all the way through the system to something we don't want. Whereas down here, we've got an AND gate. So these won't propagate up unless these two independent failures both happen at the same time. So straight away, we can do quite a lot of work without numbers. Okay, and often we really should, instead of jumping straight into numbers. Right, that's enough on fault trees. More on that later. Okay, so the 8 disciplines method is one of those. Oh no, I was going to get mixed up with something else. So introduced by Ford, and I've never used it, but it looks a sensible method. We've got the steps there. They're actually 9. You've got to do some planning. It's meant to be a team-based activity. What's the problem? Now, a nice point, number 3, the first thing you do is say, so it suggests there's some urgency here. What are we going to do in the interim to contain the problem? Okay, while we work on a longer term solution. That's really important. We need something short term in order to maybe manage the issue while we work on a slicker, more comprehensive solution. So great, let's do that first. Nice point. And then we move on. Okay, let's look at root causes and escape points. In other words, when did this get out of control? When did this get away from us? When did it escape from our control? Or, you know, what was the opportunity for it to go wrong at what point in the process? So then once we've understood the root causes a bit better and the timing issues, now we're in a position to choose and look at more permanent corrective actions. Okay, better control measures, implement them, take preventive measures. So maybe we can stop the thing happening in the first place, which would be even better. And then, as it says, celebrate with your team. Okay, so it's time to go out for a curry or whatever it might be. But what I like about this process is that it recognizes, it's multi-stage. It recognizes there might be a short-term solution. It recognizes we need more data to come up with a more elegant, permanent solution. And it also recognizes, well, maybe we can prevent this problem in the first place, not just mitigate it. So in this process, we've got preventative, mitigative controls and short-term band-aid fixes, if you like. Okay, so I think it's a nice summary, actually. Even if you take away nothing other than these are the points, I think that's very helpful. And there's more information at that link. And I will be putting out a PDF of this, so you should get all the links as well in that. Okay, so DMAIC, yeah, it's a Six Sigma process like 5 Whys. I'm actually not desperately impressed with this, because to me, sort of define, measure, analyze, improve, control, these are like statements of the blinking obvious to me. Again, I haven't used this technique, so maybe I'm being overly judgmental, but compared to 8D, I think 8D is far superior in the way it gets you to think. I think this is a much better approach. Yeah, of course, if we could define it, measure it, analyze it, and improve it, yeah, that would be great, wouldn't it? Yeah, how do we do that? No clues so far. What I think is the value add in this case is what we're doing here is a bit like, there's another paradigm called goal, question, metric. So with goal, what are we trying to achieve? Okay, so to achieve that goal or objective, what questions do we need to ask? Okay, and then finally, once we've established the questions that are cogent to what we're doing, what do we need to measure? Okay, so we might have to do that GQM thing in order to get these results, in order to measure the data that needs to be measured. Okay, so I actually think the GQM paradigm is a lot more use than DMAIC. I mean, it's a nice acronym, but apart from that, I don't think it does much. It ain't working for me. And we must remember that every time we make a measurement, that implies there is some underlying model that we are measuring. It might be as something as taking the temperature of an amount of substance. If we stick a thermometer in to take the temperature, we're going to disturb the system. There's going to be a bit of heat transfer to the thermometer, which will change the temperature of the thing we're measuring, for example. So every measure implies an underlying model. The mathematicians tell us that. So there, I think, is a bit more value add than just the DMAIC. So scatter diagrams. Now, again, a scatter diagram, rather like the Pareto, it assumes that we've got some data, okay? And depending on the kind of data that we've got, we might get a really strong, obvious relationship. So the 4 examples here, the top left one, yeah, it's really obvious there's a linear correlation there, okay, between the two variables. On the right hand side, okay, yeah, we can see there's probably still a linear correlation, but it's not as strong. And then bottom left, okay, that just looks like relatively random data, okay, or we might have a strong non-linear relationship, which is bottom right hand side, okay. And I drew in those lines, so if they're not in precisely the right place, don't worry, that's not the point. So yeah, if we've got some data, can we find a correlation? Of course, correlation does not mean causation, okay, as a colleague always used to remind me. So just because we found a correlation doesn't necessarily mean we found the root cause. There might be a perfectly logical reason why two things are correlated that's got nothing to do, you know, we can't actually manipulate the other variable in order to make a difference. So again, very useful for spotting relationships, but it assumes we've got the data. Okay, and a little bonus here, something I picked up while looking through this stuff. If you go to smartsheet.com, you'll find a whole bunch of nice templates on cause analysis reports. Okay, so I haven't been through them all, but there looks like quite a lot of good stuff in there if you're interested. So there's your 8+1. You see, I've under promised and over delivered. You can tell I was a consultant, can't you? And that is the first part of our presentation. We've got some resources here. So basically, if you want some more stuff from the Safety Artisan, go to Thinkific, and my courses are there, including all the webinars at the Academy. And if you want to try out, you get 7 days free membership to the Academy anyway. But if you want 1 month, if you want 1 month for free, use the 1 month free membership code. Okay, and there's more and more stuff in there, adding to it every month. There's also more stuff at the website. You can subscribe for free emails to hear about the webinars and other things that are going on, and you can look at the YouTube channel, and I'll share that stuff later. In fact, very soon, because I think we're coming up to our Q&A. So I'm going to stop sharing this, and just going to escape out of there. Okay, so hopefully, while you're thinking about some questions, I am going to share, where's my chat? So I'm going to activate the chat. So do please think of some questions. It doesn't have to be on causal analysis. If you want to ask me about something else, that is absolutely fine. So I'm just going to share those. Okay, so there you go. So there are all the resources that I mentioned, and I will just I'll go and dig out. I will go and dig out that bonus one that I showed you. So we will add that. So there's the smart sheet. Okay, so we got any questions, please? Take your time. By the way, let's see who else has joined us. Some familiar names. Welcome, everyone. It's good to see you. Can you still hear me, by the way? Somebody. Thank you, MC. So, okay, well, I'll let you. Oh, thank you, Cheryl. Well, I'll let you think about the questions some more. So what we will do then is we will move on. And we will go back to sharing. Oh, we have a question. The flow of preliminary hazard analysis. Okay. Well, the flow of it is dependent on which technique you use. So, and I would recommend you use several techniques. So, for example, if you use a checklist, the flow checklists tend to identify causes. So you'll start with causes and you'll work your way towards hazards. If you are looking at incident and accident data, that tends to be incident and accident centric. So it's consequences. So the consequences will get reported, and you then have to analyze the data, that whatever information you've been given, to work your way back to hazard and causation. Okay. If you're using FFA, so to do PHA, PHIA, then you're going to be looking at what can go wrong with the function. So that kind of, it leads you to what is really more starting with the hazard maybe, and it leads you in then both directions. You can look at the causes and the consequences. And HAZOP the same. Most HAZOP tables will prompt you to look at, causation. Okay, so we've got an incorrect flow. What are the consequences of that? So we're starting with causes, we're moving towards hazards, and then it will prompt you to look at preventative and mitigative measures and detection measures. So depends on what technique you're using. Okay, I hope that's what you meant by the question. If it wasn't, then do please let me know. So cheers, Chris. Anything else while we're talking about it? Okay. Well, we can have another Q&A session at the end. So, and by the way, if you think of something afterwards, send me a message, on social media, or leave me a question on the website. Oh, follow-up question. Yep, you're welcome. Which comes first in terms of hazard analysis? Oh, so I'm assuming you mean which technique. So we would start, once we've sort of set the context and understood the scope of our system, what's the system, what are we using it for, what's the operating environment. So we need to sort of understand that context first. Then the first thing we might do is some preliminary hazard ID using a number of techniques. Inevitably, identifying hazards will also help us to analyze them and will yield more data. So we won't just get hazards, we'll get some stuff about causation and consequences. And then we could also look at our system requirements hazard analysis. I talk about this, by the way, in Foundations of Safety Analysis, or Foundations of Safety Assessment, which is one of my courses in Thinkific. So I look at 3 tasks. So under MIL Standard 882, there's task 201, which is preliminary hazard ID, task 202, which is preliminary hazard analysis, and task 203, which is system requirements hazard analysis. Now, you don't necessarily do them strictly in that order. You kind of do one and it helps you, leads to the next one, and then you go back again. So you might have to iterate round a couple of times, but start with PHI. Right. Oh, right. I'm glad that's helpful, Chris. So, Cheryl, what tools suit a project approach when introducing new technology, but you do not have any data to hand at that time? But need to satisfy the project manager. Yes, always. So if you've got new or novel technology, you're not going to have, I say you're not going to have historical data. It may be that your novel technology is just a new way of doing something that, old technology does. But for something really new and novel, you're going to need to take a functional approach. Okay, so functional failure analysis will be really helpful. And you can apply that really early when you've got requirements. You don't even need a design. You don't even need a design concept. And then you can keep reapplying FFA and maybe turn it into FMEA, etc. as you go. Also, you may need to do some brainstorming. So something like Ishikawa might help you go broad and consider not just technical failures, but other things like, the management stuff, the environment, the people, the process, all that stuff. So that's good for that because it gets you to think broadly. If it's anything involving a flow, okay, even if it's software data or whatever, you can use a HAZOP or a variation on a HAZOP. I'm doing HAZOPs. I'm doing audits next month and HAZOPs, I think, the month after that. So you can do a HAZOP or you can do a control HAZOP, a CHAZOP, okay, or a SHARD for software, SHARD, software hazard analysis. Is it requirements and design? I can never remember. So there are lots of techniques out there. The key is probably to get several people in a room, people who understand the technology, people who understand the application, what are we using it for, people who understand the environment, because it's the interaction of all of those things that's going to lead potentially to problems. Okay. And as I say, when you're identifying hazards, particularly with a novel system, use multiple techniques, because no technique is perfect. Some techniques are good at this, but not so good at that. But if you use several, hopefully you'll cover over all the gaps. Okay. And again, I talk about this in PHI. There's a lesson on hazard identification. Okay. So, you're welcome, Cheryl. Right. Well, thanks very much. Some good questions. As I say, if you think of some more, pop them in the chat, and they won't go missing. I'll pick them up when we get back. So let's go back to sharing the screen, or where are we? Okay. So what I'm going to do in part 3 is I'm going to take just a little snapshot of the European Maritime Safety Agency report 2023. So it's actually talking about all of the accidents and incidents in 2022 for a 12-month period, all around Europe. Okay. And it is an excellent report. It's always been good. Some things they do better than others in certain years. So if we look at the headlines, so we're talking about a total of almost 20, well, over the period 2014 to 2022, which they've been reporting on, they've had reported almost 24,000 incidents, 2,500 in 2022 alone. So we've had 26,000 ships, 184 were lost, over 1,000 investigations, almost 7,000 serious casualties, very serious, 600 fatalities, just over 600 fatalities in that period, as almost 7,000 injuries, and over 500 pollution incidents. So there's an awful lot of data that these people have been analyzing. And of course, if you've got that much data, then you can get some statistically valid results, and you can do some really good analysis, which is exactly what they've done. So let's have a very brief look at what they've got. So in the beginning, we've got a look at different kinds of ship. So we've got cargo, passenger, fishing vessels, service ships, so maybe servicing the oil industry or whatever, and other, including pleasure craft. And so for these different kinds of ships, we've got the different accident statistics and incident statistics over the years. And as you might imagine, the dark red is a very serious marine casualty. So we're talking about ships sinking and that. And thankfully, we have very few of those at the bottom of the bar charts. And then as we move from red to pink to yellow to green, they get less serious, but in general more common, although the green get less common. That's funny. Why is that? We'll talk about that later. And as you can see, there's a lot more cargo ships out on the ocean than anything else. So they have thousands of accidents, whereas there's relatively few other ships, although one suspects that amateur sailors actually proportionally have more upsets and mishaps than anybody else. But who am I to say? So that gives us a good overview, and that's important because the operating profile of these different ships can be very different. Okay, so the way they operate, what they're used for, and as a result, the operating environment, and more on that later, will be different, okay, for each one of these types. So that's important to understand. We've got to know the context. So then we might do, here's an example of, we've looked at some basic causation, and as we can see, by human action accounts for more than half of the causation of all accidents and incidents. And then equipment failure, about a quarter, other agents or vessel, just under 10%. So actually, by the time we've got those first three types, if we do our little Pareto analysis on the right-hand side, we've got most of our causation there just in those three things. Hazardous materials, okay, we could look at that as well. But if we take those four things and the others are unknown, we've got 98% of our causation just by looking at those four things. Okay, so very powerful Pareto analysis that helps us to see this is what we should be prioritizing. This is what we should be focusing on. Now, what's interesting is I work with some clients who are absolutely obsessed with hazardous materials because of bad things that have happened in the past. We will say no more. But the thing is, they got it all out of proportion. They go nuts about hazardous materials, and they spend loads of time and effort looking at hazardous materials, whereas maybe they should be looking at human factors. Okay, first and foremost, depending on what you're doing. So certainly, if you're doing anything to do with ships, here's a good clue about what to be looking at. Okay, and this is all ships, so all different types of ships. Or non-military. And then if we look at, well, how does that vary across ships? And the answer is not much, actually. Yet human factors, okay, on passenger vessels, we seem to have fewer human-related incidents, but more technical, okay. So maybe that suggests on passenger ships they've worked a lot harder on their procedures because they've got a lot of people to protect. It's a very people-centered industry. Whereas all the other types of ship, it's in the, it's 56, 57, 58, 60% are human factors. And then on the least serious, the green incidents, well, we have none at all on other ships, which suggests to me that the amateurs aren't reporting near misses at all. Okay, no surprises there. But fishing vessels seem to be pretty good at it. I guess maybe deep sea fishing is quite a hazardous business, so maybe crews are more aware of the importance of safety because sadly they probably all know of somebody who hasn't come back. So again, there's lots of potential different causations and driving factors in here that we might imagine by looking at, but clearly this data is a bit too crude to form any, to give us any great insight, other than, generally speaking, the balance of causation seems to be much the same for almost all ships except the others. Okay. And maybe, the fact that system failures are quite low on other ships maybe reflects the fact that they're very simple vessels. Who knows? Let's move on. Now, if we actually start to look at some more interesting causation, so we've still got the same basic causes: human action, system equipment failure, other people getting involved, hazardous materials, and unknown. But now we have the breakdown of, did this occur on the ship? Was it something that happened on shore that affected ships? Or was it the external environment? Okay. And again, we see, apart from other agent or vessel, which kind of links to the environment, so that kind of dominates there, we see much the same pattern for all the basic causation contributing factors. Okay. Shipboard operations are by far the biggest contributor, particularly on human action. And they tend to dominate in most areas. Okay. Again, pretty crude, but for very little data, and of course it costs us nothing to go look at this online. It's available for free. For very little cost and very quickly, we can begin to get some insights into what's important. So let's break that down a bit further. If we look at recommendations for improvements, basically, and we look at the different focus areas, we get some clues as to root cause analysis, because clearly somebody's investigated. They've had over 1,000 investigations. Here's what they've come up with. And other safety recommendations. So the biggest one, ship-related procedures. Okay, things going wrong on the ship. Human factors recommendations. Ship structure and equipment. Okay, so that's quite important, and almost as important, other procedures. And then shore and other equipment, quite small, and other smaller still. So again, if we look at those top four, we're going to get, what's that, 95% of the recommendations. So, and again, if we, in classic safety, if we look at a hierarchy of recommended controls, we might say, okay, so ship structure and equipment, that is maybe going to cover, your engineering controls, whereas your procedures here, in the red and the dark blue, procedures are accounting for 2/3 of all the recommendations. So procedural is one of the weakest control methods, the least effective, but 2/3 of the recommendations here apply to improving procedures. So tells you something about the quality of procedures as well, doesn't it? Maybe a bit more effort on saying whether a procedure is practicable or not, whether it's actually going to work in the environment. Maybe we could put a bit of effort into that and get some really good results. Ship structure and equipment, yeah, okay, less than a quarter. Okay, human factors, now that is maybe a bit false, so we'll look at that, because all the procedural stuff will relate to human factors as well. So we've got to remember that. We've got to interpret the data a little bit. So let's go on and break this down a bit further to get some more useful information. And so if we look at the ship-related procedures, and they've done it the opposite way around. So operation dominates, disseminating information. That's interesting. That's the next most important one. So clearly we're not telling people about stuff, or they're not telling people about stuff they need to know on ships, whatever it might be. Compliance with regulations and the law comes a close third, and then maintenance, cargo, emergencies, etc. So actually safety of navigation, for example, is quite a small area. So again, we could do a Pareto analysis of this and say, okay, so if I focused on operations and making sure that the crew and people who need to know actually get the information they need, well, that could be quite a cheap way to get a big safety improvement. And of course, this is borne out in other industries as well, I might point out. So let's look at the human factors. And by the way, this is the 2023 report. The 2021 report did a much better breakdown of human factors. So if you're interested in human factors, and it doesn't matter whether it's a ship, because a ship is, it's like a floating factory, or it's a very complex piece of plant. It just happens to be at sea. Okay, so go and look at the 2021 report for better results. But here, okay, so when we're talking about human factors, not procedures, so top is training, skills, and experience. Okay, by a long way. So we can reduce risk by improving the crew's training, their skills, and obviously it's nice to have experienced crew. So we mustn't water down the experience levels too much. Okay, rookies tend to make rookie mistakes. And then management, company, and organization. Only then do we get to equipment. Okay, triggering human factors. Although, to be honest, we're not always very good at identifying equipment triggering a human error. So we'll maybe take that with a pinch of salt. And then we get into more, lesser causation or lesser contributions. But as I say, that look at the 2021 report if you're interested in this, because it is much, much better than this, much more detailed. And then, okay, let's look at ship structure and equipment on the left. Okay, ship equipment system. Okay, on the equipment side, safety of navigation comes second. That's interesting, isn't it? Then machinery, life-saving equipment, etc. Okay. Yeah, whereas stability in electrical installations, relatively rare. I don't know what VDR is, but never mind. Then we look at the right, we look at other procedures. Okay, so this is going to complement the red stuff on the procedures. Okay, other procedures, compliance, top of the list. Yeah, almost 3 times. Yeah, other, okay, so bits and pieces. There's an important other pile there. There might be multiple things in there, so maybe forget other. Oh, port and terminal facilities. Okay, study and review, etc., etc. Okay, maybe those results aren't quite as useful, except to say compliance is important, okay, when we're not talking about shipboard procedures. Which I guess stands to reason. If you're not compliant with procedures and you've got to cooperate with the shore or with other ships, and you fail to do so, you don't obey the rules of the sea, that's going to cause a problem. So maybe, some of these things are maybe not a great surprise, but it's good data based on thousands of incidents. So getting away from the old histogram charts, here's a slightly different one. So here we've got a view of traffic density in a year of sailing in European waters. And on the left-hand side, we've got all ships. And you can see in the red, we've got some very, very dense views on, very dense traffic in certain places, mainly around the coasts, but also some clear, obvious lanes that lots of ships use. Then we've got cargo ships in the middle that are clearly, going from A to B to particular places. So that's a very different profile, very different operating pattern. And then finally the trawlers on the right. And there were more than these, but I picked out 3 because otherwise they're too small to look at. And trawlers, again, okay, a very different operating pattern to cargo ships. Okay, so we see where they go in order to find the fish. And they go to some out of the way places, don't they? So, but there we go. So we've got very different operating patterns for different types of ship, okay, different environments. So this kind of information is going to be very helpful for us thinking about, well, what's the level of exposure to certain risks, okay, depending on where we're operating. And that is illustrated nicely. They looked at the 2014 to 2022 and said, okay, where do accidents happen? And about half of all accidents happen in internal water, so close to shore. Okay, now, given the fact, if we go back and look at the previous slide, given that looking on the left-hand diagram, close to shore, pretty much for every European country is red, okay, because that is the most dense traffic. There's no surprises there that there's a lot of accidents, are there? So we're colliding with other ships, we're running aground, we're having accidents. And of course, there'll be lots of kinds of ships that only operate close in, okay? So maybe ferries, pleasure craft, etc. So in close inshore fishing, etc., etc. And of course, every ship has got to go in and out of port, so at least part of the time they're going to be close to shore. So it's no great surprise that this is the profile. But again, if we know the operating profile of the vessel, we can begin to look at the sort of break down the exposure and say, okay, we spend a lot of time in the deep ocean, and that's actually a lot less risky than anything else we do, or open sea as they call it. And as always, we've got a little nugget of unspecified or other. Don't know what that is. Maybe lakes or something. I don't know. So again, more clues about how we analyze stuff. Now, finally, I've gone back to the 2011 report for a slightly different perspective, because the 2011, sorry, that shouldn't be 2011, that should be 2021 report. I do apologize. So the 2021 report actually did things slightly better. It did the human factors better. And what it also did was it set out the amount of reporting for each vessel type, for all sorts of things, in this sort of format. Okay, now why is that important? Well, if we look at the Heinrich's triangle or Bird's triangle or pyramid, what we find in general, not just in shipping, is that we tend to get an awful lot of minor things, unsafe acts, near misses. Okay, we get hundreds or even thousands of those for every fatal accident. Okay, what we tend to get, and you see this, we saw this in the data, didn't we, for all ships. You get, fortunately, you get a very small number of most serious casualties. Okay, ships sinking and people getting killed, but you get far more less serious accidents and incidents. But if we look at the reporting, so by the way, the bottom pie chart is completely separate to the top one. So here, 3%, the light blue, those are the most serious accidents. 25% less serious, but still major. And then we've got 57% effectively reportable accidents, and then minor incidents and near misses is in yellow. But look at the scale of probable underreporting. Look at that. What we should have is, instead of 16%, it should be something like a third to a half of all reports, shouldn't it? So clearly there is big underreporting going on there of the most minor things, okay? And that's why they go unreported, okay? People don't have to report them. People make a mistake and they don't want to admit to it in front of the management, etc., etc. So there's another indication that if we worked a bit harder on the reporting, on getting people to report minor stuff, on having confidential reporting, making it really easy to report something, or maybe automating it in some way. You know, we've got AI, we've got CCTV. Maybe we could dramatically improve reporting by automatically spotting problems and not relying on people. A number of things we could do. But it does give us an indication that we have to interpret the data and go, okay, the fact that we've got this number of serious incidents and accidents does indicate that there are many, many more near misses going on. And therefore, when we're thinking about our accident and incident statistics and how often causes happen, causes are going to happen much more frequently than we think they do, because there's a lot filtering them out, stopping us getting to the most serious consequences. The other thing to note, bottom left-hand corner, is who is reporting these things, okay? And what is interesting is that the ship is only reporting. Now, if we go back and we'll go back and look at how many incidents are on the ship, but the ship actually only report 11% of incidents in that particular year, okay? Whereas almost 2/3 of incidents were being reported by the shore authority, okay? And shipping companies and the like are reporting about 1/5. But the ship are not reporting very much. But we look at our causation, ship-related procedures, almost half. Ship structure and equipment, okay. Yeah, other agent or vessel here, only about 8.4%. So the vast majority of incidents and accidents are happening on the vessel, okay? And I think that's confirmed again here, isn't it? Because shipboard operations account for the vast majority of incidents, shore management and external relatively minor. And yet, when we look at the reporting, the ship are actually reporting only 1/10 of the incidents. So clearly there is massive underreporting on the ship. Okay, so there's a lesson for us. Okay, a very powerful lesson. So we're up to 1 hour and 10 now. So I just want to make a final observation. In my 25 years in the business, I've seen gigantic amounts of time and money spent doing analyses of causes of technical failures, whether it be qualitative or quantitative. I've seen so many 500-page fault tree analysis reports, FAMICA reports 1,000 pages long, and so on and so forth. And, just enormous amounts of money spent doing that. I've seen very little money spent looking at the opposite end, looking at operational accident or incident data, often which is free on the internet and is a click away. So I've seen very little analysis of technical versus operational versus human factors versus procedures, very little analysis of operating profile, patterns, environment. And yet, from the data that we've seen, even though the data isn't perfect, as we've seen, even with EMSA doing excellent reports, the raw data, massive underreporting, even so, there's a huge amount of really good data there that we could be using to set the scene, to set the context, and to be honest, to put some honesty on the conversation with stakeholders. So when stakeholders say, that'll never happen, you can say, well, hold on, in 26,000 casualty reports, it happened an awful lot. So don't tell me it's never going to happen. So there's an awful lot of use we could get out of this data when it comes to causal analysis, not just technical causes. Okay, right. I've banged on about that long enough. Quick word on upcoming webinars. So next month we've got safety audits. In March, I'll be talking about audits. I'll talk about HAZOP in April, and not just HAZOP, but shard and control HAZOP. I think we'll talk about a bit as well. Event trees in May, claim, argument, evidence, and goal structuring notation in June, and fault trees in July. And as you can see, we've already covered FAMIA, risk matrices, and hazard logs. And actually, there's a whole bunch of other webinars. There's more than, I think, yeah, there's many more than three webinars in the academy. So, right, that's the end of that. Let's go back and see if there are any more questions. So thank you all for listening. I hope you got a lot out of that. I certainly learned a lot preparing this. It really drove home some lessons that I've learned, informally in my career. Okay, so do we have any more questions? I appreciate that some of you might be typing away, so we'll wait. Let me just check. Okay, for those of you who are not in via Eventbrite, I'm not seeing anything in the chat. If you're on Facebook or YouTube, you should be seeing the chat and you should be able to respond. If you're on LinkedIn, then do please leave me a question in LinkedIn, and then I will get to it afterwards. Okay, I won't be able to do it now, but I'll get to it. So, do I consider a cause analysis as lagging indicators? Okay, to measure HSE performance, health and safety. So it depends on the indicator. I suppose all of the accident and incident data, they are lagging indicators for the people who've had the accident. But if you are trying to learn from other people's mistakes to anticipate your accidents, then they are leading indicators, aren't they? So I guess it all depends on your perspective. Yeah, I suspect, Chris, you're being bothered by people who want KPIs. They want leading or rather than lagging indicators. If you look at the causation and you can say, okay, let's say a lack of training or inexperience levels are a contributor to accidents, then you can say, okay, a leading indicator is if I track experience levels or, competency levels or what skills have we got or whatever it might be, that is going to be a leading indicator of possible problems. Okay. Similarly, some of these things are more difficult to do. So procedures, okay, how many complaint reports have you got about procedures, or how many amendments have you got waiting to be done on your procedures? Okay, so if you've got a lot of requested amendments and they're not being actioned, that means your procedures have got problems that are not being fixed, which is probably going to drive accidents and incidents, or maybe non-standard behavior, because of course if the workers know a procedure is garbage, they'll ignore it or they'll do a workaround. Okay, which means that you've got non-standard work going on, which might in itself be a problem. So yeah, so you could use in theory all of these with a bit of thought as a leading indicator. Are they considered to be benchmarking to the shipping industry? Well, certainly for Europe, yes, I would say so. The thing about the European maritime industry is it's going to be relatively modern, well-maintained ships, relatively good compliance, relatively well-trained crews with, a good regulator keeping an eye on things and shore authority. So that, as we saw from the data reporting, the ships are not necessarily playing ball, but it's a well-regulated system. Now, there might be parts of the world where if you're operating mainly, in, shall we say, less well-regulated countries with lots of pleasure craft and lots of people on the water, lots of amateurs on the water, maybe that European data isn't going to be representative. But I would think for, say, North America, Australia, where I live, the better regulated areas of the world, it's going to be representative data that you could use for benchmarking. Okay, so thanks, Chris. Cheryl, thanks for your kind words, Cheryl. With reporting, yeah, a no blame culture. Absolutely, yes. Aviation is very good at that. The other thing with aviation is motivation. When the plane crashes, the pilots die shortly before, a fraction of a second before the passengers. So the pilots have got skin in the game. Okay, so they're much more interested in safety being improved than, say, the medical profession. Okay, which is also very litigious. So people can get very, very defensive about reporting in the medical, with the result that reporting is pretty poor. So a no blame culture. Maximize effective reporting. Absolutely, yes, but challenging, as you say, very, very much so. Okay, thanks, Chris. Any more questions from anyone? If you don't have any questions, can you just give us a quick no thank you or a no? And then if everybody else is not typing away, then we will stop. As I say, thank you. As I say, if you have any more questions, go on any of the social media channels or send me an email or go on the website and make a comment or whatever it might be. There's a form submission you can do on the website that you can ask me about anything at all. Okay, I've got some no thank yous, so thank you very much. Okay, I think we're coming to an end. We've been together for an hour and 20, not including the little intro video. So thanks very much, everyone, for your time. And I'm going to bow out now and have some dinner. So I hope wherever you are, I hope you have a good day or a good evening. Okay. All right. Thanks very much, everyone.